Now let's begin the process of transformation. The first step is rename a part. So how does rename a part works? It depends on this theorem. It says that if you have variable x and y, which are quantified like fx for all x fx or for all fy, they are provable equivalent if there is no variable conflict happening among the free variables appearing in f set. Okay? It's very easy to prove. So let's suppose we assume for all x fx, so we can derive for all x fx using assumption. We can say that we can instantiate this formula, and then you can produce fy, and then we can bring back the quantifier for all y fy, and you can see that since y does not occur in the free variables of fz, the proof can be played in both directions. Therefore, it's a provably equivalent. We can also have a proof which says that you can rename the exist quantifier. Using this proof, we can actually generate a proof which says that we can rename any quantifier, okay, occurring inside the formula. So using the previous theorems, we can rename a part. Okay? So what is rename a part means is that all quantified variables have different names. Okay? So which we can achieve by simply looking at scanning the formula, and if two variables have the same name, just pick one and give it a fresh name. Okay? And this will do the job of renaming a part. For example, you have this formula. It has two quantifiers, exist x here, and then for all y here, for all y here. They are using the same name. What we can do, just simply say, okay, just scan it as, okay, this x is repeating, I'm going to use a different name here, I put w here, z here. So always pick a fresh name. This will avoid this naming conflict which we saw conditional to applying this renaming. So you can go ahead and do it and it will work. Okay, now you have renamed a part. Next thing we do is turn the formula into negation normal form. What is negation normal form? Is that all the negation symbols are sitting on top of atoms. So we have seen that you can push negation under every operator in the proposition logic. Now we have what we have quantifiers. How can I push negation under the quantifier? That is the question. And for that, we need to look at this theorem. Okay, so how can I push this negation inside? Okay, so how do I do that? So let's suppose I have this theorem of there exists an x, not of fx. I can prove it. Okay, so now I'm going to do the push. Now I'm going to prove this theorem. So let's assume not of fy, and from which I can derive not of fy, and we have to make sure y is a fresh symbol. Y does not occur in sigma anywhere. So this is arbitrary choice, we can make it. Okay. Now what do? We can draw exist and say there exists not of f of x. Okay, which we can do. Again, one needs to go and check all the side conditions are met. Proposition rules are applied to 1 and 3. If you look at this 3 and this 1, they are proving contradictory things, and here I am assuming something, so therefore I can derive f of y. Since y is a free, remember that I chose a fresh name here so that it does not appear in sigma, so now I can do for all. Okay, so that allows me to do for all x fx. We can take this and write it as a contrapositive form. Okay? And then I can see that this negation can be pushed inside. Okay? Similarly, we can also prove a theorem that if not there exists x is given to s, so we can push this not inside and I get this not. So now what we can do is we can reach to negation normal form. What is the negation normal form? Just let us remind ourselves. It is that negation is just occurring on top of atomic formulas, and since all symbols allow negation to be pushed inside, therefore we can always connect to this formula. Okay, let's look at an example. So we have this running example in which we have a negation sitting on top. If we push not inside, the first thing it encounters is implication. Okay? So how can I push inside the implication? We have seen this. A implies B, then it becomes into A and not B. Okay? So you get this formula. Now we have a not sitting in top of a for all quantifier. When we pushed inside, then we get exist quantifier and the not is inside. Okay? Now we push again because the not is in top of a exist quantifier. Then it goes to flip again and give for all W, and the not is coming here. And so now this formula is in NNF form. The next step is prenex form. What is the prenex form? Pulling all the quantifier in front. To do that, I should be able to freely introduce quantifiers and pulling them out. Okay, so let's see. We need to prove few theorems to make sure that this works. Okay, so let's suppose x does not occur in this formula f. So out of the blue, I can introduce quantifiers here. Okay, so if I have f, then I can say there exists xf, or for all xf, or in any direction. Okay, so let's see how can I prove it. So we have seen that if you have this formula, I can derive all of this formula. So well and good. Now we will see from f how can I get to for all xf. Okay, so let's suppose I have f. Okay, we can in one step for all intro we can apply. You can say that we have this for all xf because we can play out this idea of satisfying all side condition of for all. So we choose a z, which is some sense of free variable. You choose a y, which is also does not occur anywhere, and say that okay, z is being replaced in y, and then basically that is why both do not occur in f. So this just gives you f. Okay, so for all intro conditions are met, therefore you can write this. Last step is then there exists xf. Say we have to derive f. Okay? So let's see how can we do that. You have this formula, there exists xf. Then what you do, you try usual trick of exist quantifier. You assume f and then you prove f. Then I can turn this into f implies f, and now I have can simply introduce apply in lim exist, and then I get the exist xf implies f. Nicely, I have this proof because now since I have this, I can derive this using some proposition logic rules, and I got f. So I have proven then all these three can prove each other. Okay, so how can I use this fact? I can use this fact to say that if one of the formulas, right, f and g, this guy doesn't have x, what I can do is that I can push exist inside and pull exist outside. Okay, so how do I do that? Okay, so let's see. The reverse direction is trivial and it's also true even if g has x, but let's look at the forward direction and where the x not being there is irrelevant. Okay, so let's see. So the sigma proves that left hand side, and now from this I can derive that there exists xg. Okay? And because of the previous theorem, I can eliminate there exists x and left with g. Now the usual trick of exists quantifier, we assume f of x and write f of x and g, then introduce exist x here. Okay, because I can have an evidence for x, this is true, so I can just simply say there exists x, f of x and g. Now I can use for proposition logic to push the thing here and then say the f of x implies this formula. And now we can say lim exist. Now we apply exist lim and obtain this implication. Now this can prove this guy, and this I have because of that guy, right? So I can essentially derive this using propositional logic. Therefore, it tells me that I can always pull off there exists x operator, and this is true for all also, because for all you can also pull out for disjunction case. So therefore, any quantifier can be pulled out, but they cannot jump over each other. If there is a exist and then there is a all, so you cannot say all jumps over exist, that is not allowed, but all the quantifiers can be pulled out because of this theorem, right? So formula f is in a prenex form if all quantifiers of the formula occur as prefix of f. The quantifiers suffix f is called matrix of f or body of f. Yeah. Due to the previous theorem, we move quantifiers to the front. Okay, so this is allowed because of the previous theorem. Okay, so let's look at our example. Okay, so we wanted to convert this into a prenex form as follows. Okay, so first we had obtained this into NNF form. We are already there. Now what we're going to do is that start pulling the quantifiers out. Let's pick one of the quantifier, which is there exists z, and pull it out. Yeah. Nice. And pick another quantifier w, we pulled it out. Pick another one and another one. It really doesn't matter which order you pick them, as long as you don't jump over each other, it's fine. Okay, and you have a matrix. You don't need to worry about naming conflicts anymore because you have already shown that they all have been renamed apart. The previous theorem ensures that if that is the case, we have a freedom to pulling them.